So now we are going to look at one more non-destructive technique, and that is space charge measurements. What is space charge? Now, when you apply a very high electric field, and if it is typically a DC electric field, which is applied for a very long period of time in a solid dielectric material, space charge may be accumulated within the dielectric medium. Why do we say that space charge accumulation takes place? Space charge accumulation takes place by trapping. This is something that we have discussed before. Electrons are generally in the conduction band, and when they're in the conduction band, they can move through the material and be transported from one point to another. But sometimes when there are certain electrons in the conduction band, within the material, there might be vacancies in the lattice structure. There might be vacancies where the energy level is the energy difference of the energy level and the conduction band is very small. So electrons which flow into the material may give up a very small quantity of energy and come to occupy the shallow traps. I have mentioned before that when the difference in energy of the energy level, the vacant energy level with the conduction band is very small, we have what are called shallow traps. When these energy levels are much further away, closer to the valence band, then they are called deep traps. So in a material, we generally have vacant shallow traps and deep traps because of the lattice structure, because of impurities, because of material deformities. There are very often present and free when energy levels. And once we have available electrons or charge carriers who can give up a very small quantity of energy and can come to occupy these energy levels, they are trapped. So in this way, by trapping of the charge carriers, space charge can accumulate within the body of the dielectric. Now, this is a problem because when you apply an electric field across a material, the material experiences electric stress. And electric stress can cause aging of the material over a long period of time, apart from other phenomena which can happen due to electric field enhancement. However, when in addition to that, you also have a space charge accumulated, there will now be an additional electric field which is due to the space charge. So you have the applied electric field, which is the Laplacian field, and in addition to that, you have the Poisson electric field due to the trapped charges. And if the Laplacian electric field and the Poisson electric field they will be superimposed on each other, and if they are in the same direction, there will be field enhancement, which means that for the same voltage applied across the sample, a material with a lot of accumulated space charge will experience much higher electrical stresses, and as a consequence, there will be aging of the material and degradation of the material. So charge accumulates, distorts the electrical field. Local electric field enhancement may perpetrate degradation or aging of the material. So therefore, we really need to understand, we still don't understand exactly all the mechanisms by which space charge is trapped in the material or space charge is detrapped. So charge trapping process is a matter of research. And therefore, we need to understand the mechanisms related to space charge evolution. However, from the point of view of diagnostics, we need to understand that space charge accumulation can be used as an aging marker. So depending upon the material, depending upon the condition of the material, depending on the age of the material will trap more or less charge. A material which traps more charge is more likely to age faster, will have lower lifetime, whereas a material that does not trap will not face that high stresses and will be able to last longer. The lifetime will be higher. So one is the space charge can be the reason for aging. The space charge can also be an indication of the age of the material. Let us see what I mean by that in the subsequent slides. Now, what are the sources of space charge in a material? Now, when you energize an electric material, a dielectric material, there might be charge which is injected into the dielectric material from the dielectric electrode interface. So from the metal, due to processes like Schottky injection or electron tunneling, charges may be injected in the material and they can get trapped. Not only that, Due to the application of electric field, there might be processes by which charges are generated in the material. For example, if you have enough charge, charges can detrap and can travel around. There might be reactions taking place which cause charge production. There can be ionization, there can be excitation. So the electric field in itself can be a cause for charge generation within the electric field. So charge may also be generated within the dielectric volume under application of electric field, and space charge accumulation may take place through trapping in the dielectric volume. Now, once charges are available, so charges are injected, charges are generated. That's not a problem. The problem is when these generated charges or injected charges do not flow out of the dielectric from the other electrode, but get trapped in the material. Now, what causes or what determines how much space charge will accumulate? This can be governed by many factors. The propensity for space charge accumulation may be governed by various factors. It can depend upon the applied field strength. It can depend upon the specimen temperature, the material composition, the electrode material, the material condition. All these things can determine the amount of space charge that will be trapped. Because specimen temperature, field strength, these give energy, this introduce energy into the system, and this energy can be used up by the particles for various purposes. This is a schematic which shows the pulse electroacoustic system. What you have is, this is your high voltage electrode, and this is your high voltage electrode, and then you have the sample. And then you have the ground electrode. So between the high voltage electrode and the ground electrode, you have the sample. This comes in an electrode enclosure. As you can see, there is a supply, a DC supply, which energizes the sample. Apart from that, you have a DC pulse you have a pulse generator. So there are two supplies, two fields that are applied. First is the continuous DC voltage which is applied across the material, which can be plus minus 30 kV. This is what we have. Depending upon the thickness of the material, the field across the material will change. And additionally, we have a pulse generator which sends a pulse through the material. Now, depending upon the condition of the sample, what really happens, of course, this is a system where the pulse is taken out. Now you have here near the ground electrode, you have a piezoelectric transducer. So what happens is, when you energize the sample, space charge accumulation may occur inside the dielectric material. Now, depending upon the space charge location, when a pulse is generated and sent through the material, the pulse will interact with the space charge that is accumulated, and as a result, this pulse, which sends an acoustic wave through the sample, will be modulated in such a manner that the space charge quantity and the location of the space charge along the thickness of the sample will modulate the acoustic wave. Now, this acoustic wave travels through the sample, through the ground electrode, and is picked up by the piezoelectric sensor. So, the signal from the piezoelectric sensor has an information about the space charge location as well as the space charge magnitude. So the total space charge that is accumulated within the material. Now, there are actually various techniques for space charge measurement. We are going to talk about only this particular system, which is the pulsed electroacoustic system, where the acoustic wave is generated due to the presence of space charge. This acoustic wave is collected by the piezoelectric sensor and converted into a voltage wave. This voltage wave carries information. This voltage wave carries time domain information about the space charge. So the wave that comes is modulated by the presence of space charge, and the time at which the space charge signal, the signal that is modulated due to the space charge, arrives at the sensor is related to the velocity of the acoustic wave through the sensor, and that time information is converted into spatial information. So if we know the velocity, we would know how the signal is modulated and how long does it take for the signal to arrive at the sensor. So that will give us spatial information. So there are very few techniques. There are indirect methods of space charge measurement. In fact, we have talked about polarization and depolarization current measurements in the earlier lecture. That can also be used to measure space charge. We can use electroluminescent techniques to measure space charge. So there are very many techniques that are available. But this pulse electroacoustic system I am discussing separately, specifically because it gives us an additional information. It does not only tell us how much space charge accumulation takes place. It does not only give us information of the magnitude of the space charge. It also gives us information about the location of the space charge. In fact, what you have is you can obtain a one-dimensional map of the space charge within the thickness of the sample. So you have the sample and you will know how exactly the space charge is distributed along the thickness of the sample. We use parallel plate electrodes, so there is only one-dimensional variation. We cannot have two-dimensional variation. This is the photograph of the pulse electroacoustic system from TechM that we have in the high voltage laboratory in IIT Kanpur. Here you have a DC power supply. This is the PES cell. In the PES cell, you have this entire assembly of the high voltage electrodes, the ground electrode, the piezoelectric sensor, and a pulse generator is there. The pulse generator injects pulse into the sample. The signal, the voltage signal, is registered in the oscilloscope. The voltage signal has to be calibrated so that it can be converted into equivalent space charge map. So what we do is very similar to the polarization and depolarization mechanism. We apply a voltage across the material so that space charge trapping can occur. After that, we short circuit, we de-energize, we switch off the power supply. It is seen that after 20 seconds after voltage off, the charge distribution principally corresponds to space charge accumulated in the material. Now here we are talking about a particular system. We are talking about an epoxy resin sample that we used, and we have to wait for 20 seconds before we can make any measurements. For example, if you look at this signal, this is the signal, the depolarization signal. That means the charge has been trapped and we have just removed the supply so that the charge has not had time to detrap. When you remove the energy, when you remove the supply source and you short circuit the specimen, then the trapped charge will flow out and it will be, it can be registered. The charge will continue to dissipate with time. What we are doing is we can also make space charge measurements during the energization portion, but we can also make measurements right after depolarization begins. And this is convenient because it helps us to isolate the signal which is only due to space charge. So for example, when you see this signal at 10 seconds, we see two things. We see that the space charge, so this is the space charge density. The space charge density in the thickness of the sample towards the center of the thickness of the sample is 0. So the space charge is accumulated near the electrodes. But there is something else happening, and that is at 10 seconds, we see that there is some charge which is on the electrode and there is some charge which is just next to the electrode. So here we also have some polarization charges. We have polarization charges which are present and which will be registered in the signal. So we have to wait for a sufficient quantity of time. The sufficient quantity of time depends upon the material in question. Once we wait for sufficient quantity of time after switching off the voltage, the polarization charge will disappear and you will be left only with trapped charges. These trapped charges are, of course, only at the electrode for this kind of a sample, the sample measurements that we are seeing here. And this is an unaged sample. So we wait for 20 seconds after volt off before we make the measurement. And that gives us the signal only due to space charge accumulation. So this demonstrates the need to wait a minimum time after volt off before beginning of measurements. So this is such a short time that depolarization or detrapping of charges have not yet begun. You have the enough trapped charge, but you do not have the effect of the polarization charges. So trapped charge density can be calculated by calculating the area under the signal. So QT is equal to 1 by L integration QP XTT dx dl. So you integrate over the entire length, the area under the curve of the entire signal to get the total charge density, which is trapped. As we see, this is homopolar charge transport. Homopolar charge trapping has occurred in the sense that negative charge has been trapped near the negative electrode and positive charge has been trapped near the high voltage electrode. We have applied here a positive signal, so high voltage is positive with respect to ground. And QT as a function of time is given by the integration quantity, but QPT, the signal as it is, gives the space charge distribution between electrode position O and L. So these are the two electrodes. This is the ground electrode and this is the high voltage electrode. So this needs a calibration. This needs some demodulation techniques so that we can convert the voltage signal that is obtained at the oscilloscope into the corresponding space charge signal. Now, to show, to get an idea about what are the factors on which the space charge depends, here we see the field effect. On the same sample, various quantities or various magnitudes of electric field, DC electric field has been applied. 30 kV per millimeter, 40 kV per millimeter, 50 kV per millimeter. And we can see that as the applied field increases, the space charge density also increases, which means more and more charge is injected into the material and it is trapped. Of course, the amount of charge that will be injected at an electrode dielectric interface also depends on the material of the dielectric. So if you use gold instead of aluminium or similar such thing, depending upon the work function of the electrode material, you will have more or less charge because you need energy for charge to be injected. An increase in the applied field causes charge injection barrier height at the metal dielectric interface to be reduced, thereby increasing the amount of charge which is injected into the dielectric. And if you have more charge being injected into the dielectric, the probability of more charge being trapped is also more. So as I said, one thing can be done is you increase the field. A similar effect could be had by changing the electrode material. Because some materials require more energy for charge to be injected. Material effect is also there. For example, if you use polyethylene instead of epoxy. Now here there is an important factor that I want to point out. We apply various electric fields and we measure the space charge. And we see that the space charge density varies with the electric field. Now at a certain voltage, we see that this plot shows a drastic change in the slope. Both epoxy and polyethylene shows that. Now this point, this voltage or field at which the slope of the charge density versus electric field curve suddenly changes and becomes much steeper is called the threshold field. The threshold field is essentially the field which a material needs for sufficient quantity, significant quantity of space charge to be trapped. So essentially, if you're working below, and there is also a point of view that below threshold fields, no aging, no space charge accumulates, and if no space charge accumulates, no electrical aging either occurs, which means that if you're operating a material below its threshold field, you don't really have to bother about its lifetime because there will be no electric aging. Of course, this is not entirely true. There will be other factors which will drive aging, but the electrical aging will be insignificant. Whereas the moment you cross the threshold field, charge trapping occurs, and if you go to higher and higher fields, more and more charge trapping occurs, more and more charge in the material will cause faster aging and reduce lifetime. So we would always like to design our apparatus such that we operate our insulation below the space charge threshold field. That's one aspect. The other aspect is if you want to figure out which material has a greater propensity to space charge trapping, you will have to operate at fields beyond the threshold field to be able to compare. So that is what we do here. We compare two materials, epoxy and polyethylene, and it is seen that the polyethylene has a lower threshold than EP, which means that polyethylene will be more likely to age at the same electric field, and therefore it will have a smaller life. PE measurements, which I have not shown here, PE measurements show a higher trapped charge density in polyethylene. That makes sense. If charge begins to accumulate at a lower voltage, it makes sense that you will accumulate more and more charge, but this is not always true. Later, when we talk about nanodielectrics, you will see that nanodielectrics have a lower threshold field, but beyond the threshold field, charge density is lower. Conduction current measurements show a lower conduction current density in polyethylene. So, as I said, PE is one of the mechanisms by which space charge measurements can be done. You can also make space charge measurements by using conduction current. And in polyethylene, we see that there is a lower conduction current, which means less current is flowing. Less current is flowing means there is a greater quantity of space charge. Thus, we see that a lower mobility in polyethylene is that the lower mobility of polyethylene is associated with higher charge trapping. So, this is to show that the fills, the material, all these determine the amount of space charge that would be trapped in a material. But lastly, we come to the most important point, the condition of the material. Even if you have the same material, the composition of the material, of course, will determine the space charge trapping. But even if you have the same composition, the age of the material will decide the amount of space charge trapped. And therefore, it has been proposed that the space charge density can be used as an aging marker. So you can use the quantity of space charge trapped to figure out which material is more aged. Let us see what is the basis of this conclusion. So for example, here we have a unaged epoxy, which is what we had been working with so long. So this is the unaged epoxy. As we can see that it has a very high threshold field. But then we have the same epoxy, which is aged first at 15 days at 100 degrees centigrade for 15 days. And then it is further aged up to 30 days. So this is after 15 days. This is after 30 days. Thermal aging is being carried out at 100 degrees centigrade. So what you see here is after 15 days aging, the threshold field has decreased. And in this case, after 30 days aging, the threshold field has decreased considerably. So that means with aging, the material is becoming much more increasing its propensity for space charge trapping. It will allow space charge accumulation to happen at lower fields, and therefore it will be more vulnerable to aging. Now, if you look at the actual space charge density map for the aged and unaged epoxy, so the unaged epoxy, you have the solid line, which you can see is the smallest. So you have a very small peak near the electrodes, and there is almost, as we have discussed before, there is almost no charge trapped within the volume of the dielectric. Again, you see some space charge trapping at the location of the other electrode. So space charge in an unaged sample, in a virgin sample, space charge trapping is limited to the location of the electrodes. And further, the quantity of the density, space charge quantity magnitude is also pretty low. Now, when I take an aged epoxy, this is unaged epoxy, and then we have unaged polyethylene. Now, as you see this dashed line, this is also virgin sample. Polyethylene, as we have discussed before, has a lower threshold field and higher charge density trapping. So we do see that at the electrodes, the polyethylene shows greater charge density. However, both the virgin samples show no space charge accumulation in the volume of the dielectric. Again, here you have at the other electrode, epoxy has low charge density, polyethylene has higher charge density. So it is material dependent, but none of these samples, neither of these virgin samples, show any kind of space charge accumulation through the thickness of the material. Now, when we take aged polyethylene and aged epoxy, both thermally aged at 100 degrees centigrade for 30 days, so equivalently aged, we see something very interesting. The first thing that we see is in the aged epoxy, we see there is the space charge accumulation has increased considerably even at the electrode locations. And not only that, there is a considerable space charge accumulation in the volume of the dielectric in the region between the electrodes. Originally, we did not have any charge trapping in this region. However, with aging, there is a considerable amount of charge density, charge being trapped through the entire volume of the dielectric. A similar thing is seen with polyethylene. Polyethylene is this one. So here you see something interesting. Polyethylene also, you see that the charge density at the electrodes has gone up, but here it has not gone so much as here. And also, in this case also, you see that there is considerable charge trapping within the volume of the dielectric. I'm not going to discuss about the polarity of the charges that are happening in the volume of the epoxy and polyethylene. That is, beyond the scope of this lecture. But the point that I'm trying to make is both virgin samples do not show any kind of charge accumulation through the volume of the dielectric. So any kind of degradation that you expect will be limited to the near the electrode regions. However, when you use the aged material, be it polyethylene or be it epoxy, you can see that firstly, at the electrodes, the charge accumulation increases. And it may also not always be homocharge accumulation. The charge polarity may change. And change in polarity may cause the local field enhancement in a different manner. And most importantly, in aged samples, you see considerable amount of space charge trapping throughout the volume of the dielectric. And if you then if you compute this charge density by integrating these curves, you can see that with aging, the space charge density of the material will have gone up considerably. So therefore, space charge density can be used as an aging marker. Once you have the baseline for the virgin samples, the threshold field goes down with aging and the charge density map changes completely with aging of the sample. So in this way, space charge techniques are now being looked upon as a diagnostic tool for HVDC insulation.